All right, so we have it set up now where we keep clicking the button, it kind of moves through the parts, right? And then at the end, it clears the op stack. And then we start doing math. So I think we were, processing output queue. So as long as there was still stuff in the output queue, so the idea here is that when we process the output queue, we're doing this similarly to what we did before, where it was one move at a time, right? So click it, pop something off there. If it's an operator, do some math, blah, blah, blah. All right, so we'll get the first thing of the output queue. So this gets the actual value. This removes it from the, this gets the value. This gets the temp view. This actually removes it from the output queue visually. Right, so every single step we take here, there's kind of 3 layers to it, right? One layer is get the value. Another layer is preserve the view. And then the last layer is remove that view from its previous container. So those last 2 steps all have to do with what the user sees. The first step has to do with the data we're working with. Make sense? All right. So then if we're not dealing with an operator, if we're not supposed to do math, go ahead and toss this dude onto the solution stack. Okay. So this is the data version of our solution stack. This is the visual version of our solution stack. And what we're pushing on there is not a node, it's the string representation of our number. Okay? So the idea is we might have 5, then 4, then plus. So we get a 5, throw it on the solution stack. We get a 4, push it on top of the 5 in the solution stack. We get a plus, now we do math. That's when we get into this else. So we'll go ahead and get num1 and num2 from the solution stack. And we'll turn those guys into integers. So we'll parse the int out of them. Then we'll go ahead and visually remove those guys from our solution stack. And notice I didn't preserve those views because I don't need to preserve them because I'm going to be creating a new answer and then creating a new text view out of that answer and throw it into the solution stack. That makes sense? Okay, so that's why I'm choosing not to preserve those couple of views as I remove them from the solution stack. I don't need them anymore. We'll just let garbage collection take care of them. Okay, so this will visually remove them from our solution stack. This gets me the actual numbers to work with. Then if it's an addition, I'll do the addition. So I create a brand new label. I get my answer, which is the sum of those 2 numbers as a string. Set the text to it. Go ahead and throw that back onto the solution stack as a number. Well, it's a string representation of a number. And then also give us the visual representation of that on our solution stack. If it's minus, do the same thing. If it's multiplication, do the same thing. If it's division, do the same thing. Make sense? All right, and we're only going to do this. This is going to be every single time we click the process output. Well, every single time we call process output queue, which is going to be related to us clicking that button. This is only going to work if there's something in the output queue to process. All right, eventually output queue is going to be empty, and we're going to be left with 1 value sitting on our solution stack. All right, so let's make sure that we have a button that calls that guy. Okay, so here's our step input queue button, and then here's our process button. So this processes the expression, and process the expression. What was this guy? That's process output queue. Oh, process expression is the one that does that without doing step by step, right? So if I go to shunting yard, yeah. Oh, process expression does the, it clears everything out and reads in from our input edit text, the new expression, and loads everything into the input queue. All right, so right now we have the ability to read stuff from input text box into input queue. Then we have the click this button over and over and over again to process the input queue. Now we want to have a button that allows us to click over and over and over again to process output queue, right? All right, so we'll do a public void step output queue button pressed. This will be view v, and we'll say sy dot process output queue. This is what that guy will ultimately do. Okay. Now I'm going to actually try an experiment here real quick. I'm going to run this real quick. Then I'm going to go actually hook this up as a activity, or hook this up as the on click, hoping that that gives me an Emma for the on clicks. I don't know why this is loading. How many of you are planning on coming to the bootcamp thing tonight? Okay, so I think we're going to end up being in the room down the hall instead of here. So just kind of come in here and figure out where I am. We're going to be spending, I think, the first 2 hours on iOS. And then the second 2 hours, ish, might end up being less than 2 hours, but whatever, on Android. And for both apps, what we're going to be doing is we're going to be looking at basically a table view, an input form, and storing stuff in a database. So the table view is going to show you a list of crap stored in the database. Adding, and then your input form is going to be add stuff to database, go back to other screens, see it's added to your table view now. So kind of interacting with a third-party database and working with two kind of common widgets in both mobile application platforms. So that should give you a decent overview of stuff you'll need for the hackathon. Oh, missing return statement. This guy's supposed to return a Boolean. So inside, oh, there's my return. That's inside the else. All right, so I'll return true when I add something there. I'll also, and this is actually sort of kind of a waste, but whatever. We're actually only going to do it when we actually do some math. So I'll return true inside of each of these, just in case if they give us an operator that isn't a real math operator, we won't do something. We won't advertise that we did something. Well, he's not still upset, is he? Oh, because it's all inside an if. So this just needs to be a return false there at the bottom. If I'm still kicking here, that means I didn't try to do anything, so I'll return false. Because up top, I only do this if there was anything inside of my output queue. Now he's happier. Okay, so we'll do 123 plus 4 times 2 minus 8. So we'll go ahead and parse that expression, step the input queue. All right, and I can keep clicking if I want. There's nothing else to do. So now we want to go ahead and add a button that just keeps calling our process output queue or step output queue over and over again. So we'll add another button here. And the hope is we are then done. All right, and this guy is going to be step output queue. And then his on click will be step output queue button pressed. Okay, And let's see what goes now. Parse expression, step. All right, so I don't remember what our first two values were. Oh, 123. So there's my, it's right up there. So there's my 123 on the solution stack. We popped off our output queue, a 123, noticed it was a number. What do we do with numbers? We just push it onto the solution stack. Now I'm going to step again. So we popped off a 3. We went ahead and pushed that onto our solution stack. We probably want to make these look a little nicer, but whatever. So now I have two things on my stack. The top of the stack is a 3. Right underneath it is a 123. Then I'll go ahead and pop off of my input or my output queue the minus. Obviously, no, not the minus yet. The 2. Then I'm going to do the multiplication. So there's my 2. Now I'll pop off again. So it's going to do multiplication. So it's going to pop the 2 and the 3 off. Multiply them together, giving me a 6, pushing the 6 back on. All right. So there's our 6. Then we're going to pop off the plus. So since that's an operator, it's going to pop off the 6 and the 123. 6 is num2. 123 is num1. It'll add those two guys together, and it'll give us 129 pushed back onto the solution stack. So there's our 129. Then we're going to pop off an 8. It's a number. Push it onto the stack. So we'll have an 8 on here. Then the minus. So we'll have an 8 and a 129. This is num2. This is num1. So this would be 129 minus 8, which should give us a 121 left, right? There's our 121. And then I can keep clicking if I want, but that's our final answer. So there's shunting yard, paying attention to order of operations, blah, blah, blah. Questions, comments, concerns about that guy? And we probably can make it look a little nicer for, you know, I guess spacing purposes. Wonder how we can do that with our labels. What might look reasonable? We could certainly, when we create a number, we can certainly put a maybe a space after that, maybe a vertical bar in a space. That might look okay. Let me steal this. We also need to do it when we first process this. Actually, because we're going to be doing this to everything, what I'm going to do is up top here, we're going to go ahead and create a private string, maybe called spacer, and we'll set that guy equal to our best guess at a spacer. That way, if this doesn't work out so well, we can just change it in one place and don't have to hunt through our code, changing it in 30 different places, okay? So we'll go ahead and concatenate our spacer on to all of these guys. So whenever we create a label, we'll concatenate on spacer. All right, so that guy should already have his spacers because that's on process expression. So we've given them spacers. Spacers come with them now at that point. That's a plus spacer. That's a plus spacer. That's a plus spacer. Okay, so let's see what that ends up looking like. (123 plus 8 times 2 minus 4 parse expression). Okay, so that looks better, right? At first stab. All right, so step input queue. All right, that looks all right. There's our op stack. All right, so far so good. Yeah, definitely better. All right, call that good. I think I gave us the right answer, didn't it? 8 times 2 is 16, plus 123, minus 4 is 135. All right, so we can call that good. We'll call that done. Everybody's happy with that implementation, so let's go ahead and commit and push that. Upload it to the App Store, make zillions. Actually, we legitimately could upload that to the App Store as like it should be a free app, as more of an example of shunting guard, but maybe we'll do that one of these days. Let's commit changes. This is code from 4.4. Commit and push. Okay, so we're good there. All right, so now let's talk about binary trees. I think I gave that to you as a reading assignment, right? Okay, so everything but not AVL trees. So basically you read about trees in general, you read about binary search trees, but nothing about rebalancing trees. But did they talk about balancing issues with trees? Okay, so tell me about that. What are the when I say a tree is out of balance, what does that mean? What does it mean for a tree to be out of balance? Okay. Can we guarantee that a tree is exactly in balance? So really it's you kind of give yourself like a one level wiggle room, right? So we'll let one side be a little off because depending on the nature of the data you're storing, you might not be able to get it exact, right? So we're out of balance if one side of the tree is greater than one bigger than the other side of the tree. Something like that. You will find some self-balancing algorithms will assume that it's only out of balance if it's like 2 or even 3 bigger on one side. Why do you think that is? When I say self-balancing, what I'm saying is, what I'm talking about, this is kind of more foreshadowing for the AVL stuff, but when you add something to the tree, after the add, it says, is this tree out of balance? If it is, it rebalances the tree to get it back into what its definition of balanced is, whether it's within 1, within 2, within 3. Why might a self-balancing algorithm choose to be more lenient on the when to actually do a rebalance? And actually, before you answer that, what's wrong with the tree being out of balance? Go ahead. Okay, so depending on the datum that you're searching for, if you don't have kind of an equally balanced tree, you might run into the average search time might not be very good. Sometimes it might search really, really quick, right? If you just happen to go down the short side of the tree. Okay, no offense from that. Well, we need somebody. A couple of years ago, we had. Anybody in here know Jake Wirt? He graduated a couple of years ago. He would usually sit right here in class, and he at the beginning of class, or I don't know why this came up, but right at the beginning of class, as soon as I hit the record button, he had a sound thing that played like a gong going off. So that was always the first sound that was on the recording each class. I don't know why that came up when I was thinking about, short people like you, but maybe. Yeah. I don't even know. Yeah. Yeah. So, if you got lucky and went down the short side and that was the value you were searching for, then it would be a quick search, right? But what we're looking at is if we're going to use a search tree, which anybody, I don't know if the book talked about this, but anybody know what is a common computer science-y application that trees are used for? Well, we're saying the word search pretty often, right? So is there an application in computer science where we might be searching stuff fairly often? What databases? So databases are implemented in terms of trees. Okay, and one of the things that databases do, now different databases do have their own proprietary algorithms for speeding things up, right? So, what we might talk about is kind of the baseline of, a pretty fast average search where, somebody like Oracle always brags that they have the fastest average search time. That's their thing. So they use some sort of probably artificial intelligence based on what are common requests, and they possibly use time travel. I don't know what, who knows? Who knows? I'm not sure if they're working with Apple or not, but so they might not have access to the time travel stuff. The time travel API. At some point in time, pun intended, that's going to be a real phrase that won't be laughable. The time travel API, right? Or at least it could be. It's plausible. But in any case, database management systems like Oracle or SQL Server or MySQL, these guys are implemented in terms of tree data structures. And at the baseline is they're going to definitely have rebalancing under some conditions to give the average search time through the data, a consistency. So one search doesn't take significantly more or less time than another search, even if that means sometimes a certain search actually ends up being slower than it could be if the tree were shaped a little differently. Kind of makes some sense? All right, so now having said that, might we say that the best average search time would probably come from a tree that's as close to perfectly balanced as possible? If we're trying to really make every search pretty much on an even keel, having them perfectly balanced would be best, right? And since we pointed out that maybe perfectly balanced might be tough, or let's just say tough, within one, we're going to call that balanced, okay? Why might some algorithms choose to let it go to 2 or 3?
You have a lot of data, and you're rearranging it with every time something's added or is looking at that, potentially could really slow it down.
Yeah, rebalancing is really, really expensive. Now, having said that, to rebalance you're not necessarily saving yourself by letting it get within 3 out of whack. But what so it depends on the nature of your data and how the database is being used, and also the type of horsepower that you have. If you have a whole bunch of machines where you can offload the rebalancing to the rebalancing servers, where you can still maintain your current tree, and rebalancing servers are rebalancing, so any searches that are going to happen in the meantime can still happen, and then you replace your search tree with the now rebalanced tree, making sure that nothing new was added, so you have a lot of other things you now have to take into consideration. Then you might choose to rebalance after each entry, just to make sure that you're always optimized. But if you're working off of less horsepower, you have one machine that's performing all the tasks, it has to do the rebalancing, plus it has to serve however many users who are making queries and things like that. And this isn't something that's like an Oracle. It's some MySQL database running in a dentist's office or something like that, where we're not dealing with thousands and thousands of simultaneous hits. If that's the kind of animal that we're dealing with, Then they might say, look, we'll let the tree get a little wobbly. Okay, not the end of the world because it's going to artificially slow things down to rebalance it, and we're not really gaining that much from it because computers are fast. All right, so really we want to think about that idea of rebalancing as the more of an ideal situation. The reality is I'll pull a number out of the sky. It might not be based on fact, but it's probably close enough. Let's say that 99% of database-based applications, it wouldn't matter if you had the most unbalanced tree or the most balanced tree from a human perspective for search time. Make sense? So if you're writing your plain Jane averagey application that's not serving, millions of simultaneous hits with all sorts of users that demand real time, blah, 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 and it's scientific, simulation stuff, and asteroids might hit spacecraft because of a little bit of delays, you probably don't need to rebalance, right? Kind of like how many of you have had the database class, 430? A couple of you? So in that class, you talk about normalizing databases, right? All right. Now, normalizing a database is kind of like rebalancing a tree. Okay, it's, in the ideal world, it's a great idea, but man, it's boring. Who wants to normalize a database? Okay, but every now and then, if you're doing something legit, okay, you're working on a large project where, it's not 5 people using your software, it's 5,000 people using your software or something even bigger than that. Things like that start making a difference because, 2 or 3 microseconds difference over thousands and thousands of iterations start turning into noticeable time. Make sense? But usually when we're writing software and we're having a database, the database is for the local user, correct? Take the hackathon, for example. A lot of the different teams are going to probably be having, user accounts or something like that, where they're storing, little profile data, first name, last name, age, that kind of stuff. Well, so the user logs into their app. You're going to say, give me the data for the dude who just logged in. Okay. If it takes, the amount of time on the database that it takes to query that is negligible compared to the amount of time it's going to take to transfer the data over the internet. Okay. So if it takes an extra quarter of a second or something like that, it doesn't matter. If it takes 5 minutes, that might be problematic, right? That would be a situation where you've decided to, instead of using a database, known database API or something like that, you instead decide to implement a flat file database of your own. You just have a file that lives up in the cloud and you go, and it has millions and millions of accounts because there's some sort of virus out there that's creating accounts and everything, and you're just doing a linear search. Is this the guy? Nope. Is this the guy? No. Is this the guy? Nope. And it's file I/O, which will also be slow. How many of you have had the operating systems class? 350. Okay, so one of the things you talk about in there is I/O is slow. Okay, and we've seen it in here at least a couple times where I've done a program that counts from 1 to 1,000,000 and it happens instantly. And then I did the same program where it prints out each number along the way. Doesn't happen so instantly. I/O is expensive. Okay, that's printing to the screen. Okay, so you can imagine that just putting some text on the screen is probably a lot faster than reading stuff off a hard drive, right? So now take that to the next level. So flat file databases, which were kind of our original databases, are slow. But you know what? For most of our applications, it's probably good enough. How many of you have heard of a database called SQLite? How many of you have used SQLite before? Okay, well, what do you know about SQLite? What's good, bad, whatever?
It's a very small, lightweight database that's not designed to hold a ton of information. I believe originally it was actually designed to use phones.
Yep.
But so it can be a little bit slower sometimes depending what you're doing, but it also can be.
Yeah, really their recommendation is for a single user database, right? Okay, so, and it's implemented in terms of flat files. It's a file that's behind the scene. Okay, so they have a single file that has all your data in it. Okay, they support SQL because people want to make SQL queries. So like, okay, you give us your little SQL query, we'll process it. It doesn't support all the zillions of SQL commands, but it supports most of them. Most of them that matter, the ones that you use on a common basis for a web application or something like that. And it's fast enough. You're not going to notice the difference. But it's going to be problematic if you start having 5 or 10 people hitting it at once because it's based in file I/O, where higher performance databases like an Oracle or something like that loads large portions of the data into memory. Reading from memory is a lot faster than reading from the hard drive. Make sense? Okay. But for us, 99% of the time, it doesn't matter. You don't need to care about performance. But we should still know about performance for that 1% of the time when it does matter. Does that make sense? So I guess the lesson I'm trying to teach you here is one problem that fresh computer science graduates run into is they try to do overkill to impress their early bosses or something like that, right? It's like, well, we need to optimize this and blah, blah, blah. And it's like, okay, well, your boss is paying you an hourly rate. He wants it done. Okay? He doesn't want it optimized. If it needs to be optimized, he wants it optimized. But he just wants it done in the minimum amount of time that it takes to do it correctly. Does that make sense? So don't spend time rebalancing trees or optimizing stuff or coming up with super, elegant, fast solutions to a problem that you can. Don't spend 2 hours on something that you can solve in 20 minutes in a straightforward, brute force way or something like that, unless there's a good reason to do it. Make sense? And a good reason to do it isn't because that's what the cool kids would do. A good reason to do it is because the users will notice performance differences. All right. So, rebalancing a tree is something we want to do sparingly. That's kind of, going down the path there. But if we're just talking about trees in general, let's talk about a binary tree. And then the corollary to this would be a binary search tree, a BST, which is a binary tree that we intend to search. Okay. What are the telltale signs that we're looking at a binary tree? What are the rules associated with a binary tree? I assume that was in the reading, binary trees? Of course, I do all the reading before I sign it to you. I spent the Christmas break memorizing the book, that when we come here. So what's a binary tree? Okay, so when you think about binary, that's base 2, right? Base 2. So binary tree is a tree that every node has a maximum of 2 children. Okay, so you can have 0, 1, or 2 children for every node. So if we were to look, so here we might say, now, can you have a binary tree that's completely empty? Is that allowed? Yeah, you don't need to actually have a root node. It might not make sense, but it has to start somewhere, right? So if you're going to create a tree to hold some stuff, well, before you put the first stuff in there, it's going to be empty. You're not going to have a root node. And when you first put your first thing in there, it's going to say, there is no root node here, just like there was no head to the linked list. So we'll go ahead and just put that guy right at the top. There's, Trump would say, the tippy top. Right at the tippy top. Wasn't he talking nuclear weapons? He was talking about that one for. So in any case, it's 0 or more nodes where each node has 0, 1, or 2 child nodes. Okay? And so when I say leaf node, what does that mean?
Node without child nodes.
Yeah, nodes without children are leaf nodes. And, that's kind of maybe a somewhat unimportant thing other than just naming stuff. But, when you look at a tree outside, when you see a leaf, you don't expect branches to come off leaf, right? That would be weird. Okay, usually you have leaves that come off branches, but not branches that come off leaves. That's sign of the apocalypse type of stuff. Well, I guess no more so than a tiger eating the bad guys. Okay, so we have 0 or more nodes where each node has at most 2 child nodes. Okay. What else can we say about a, okay, so we might say it's a binary tree in general. Now, when we start thinking about it in terms of a binary search tree, what other rules then come into play? Go ahead.
Binary search tree nodes to child nodes to the left of whatever connects are going to be less than that node to the right.
Okay, and somewhere there's the equal sign, right? So either less than or equal to the left and greater than to the right, or less than to the left and greater than or equal to the right. That way we can put in duplicates, but so the point is, so typically if we're going to create a binary tree, when we add stuff to that binary tree, we're going to be adding them not just haphazardly. We're dropping. If you've seen, is it The Price is Right or Let's Make a Deal where they have Plinko? Price is Right. You seem very confident of that. You still watch that show? Yeah, I get it. Yeah, you get all defensive. Okay.
When I'm watching like 100 a day, there's nothing else. So I only have.
You shouldn't be watching cartoons. How old's your daughter? That's cartoons.
I can't stand some of the cartoons.
Is this your first kid?
Yes.
I don't have any, but I have 2 nephews. Well, I have 3 nephews and a niece. But my brother has two boys, and yeah, this is going to be not your decision pretty soon. Yeah, 10 months. I don't really care, right? But yeah, between about 1.5 years and 12.
I'm stocking up on all the old people stuff I used to watch, so I can show those to her first before she gets to the.
That's not going to work. As soon as they start mingling with other kids, you are done. Funny thing is, my brother never actually stopped watching cartoons. Now it just seems less weird because he watches it with his kids. But then again, I play with dolls, so I mean, there's a genetic, zig when there should have been a zag, I think. All right. So she mentioned that when we add nodes, I was pointing out like Plinko, right? Okay, so you drop a node into the top of the tree, and you're trying to find a home for this guy, and we're not doing any rebalancing stuff. So the tree is going to look the way the tree is going to look, and it's going to be the way that tree is going to look is going to be based on the order in which we put things into the tree. If we have the same 10 elements that we add to the tree, it will produce different trees. Well, it will likely produce different trees depending on the order in which we add them to the tree. All right. So when we drop a node into the top of the tree, it's going to try to add itself to the top, the root node, right? If there is a root node, then it's going to say, okay, am I less than or equal to this guy? Let's do that. Let's say the stuff to the left is less than or equal to. If I'm less than or equal to this guy, then I'm going to drop over there. Okay. So we're going to add to the left side, we'll say. Okay. Then if that's open, then we'll add there. Otherwise, is it less than or equal to that guy, or is it greater than that guy? So on and so forth to finally find a home for this guy. Okay. So when we add nodes, all nodes to the left of a node, let's say all child nodes, are less than or equal to it, and all child nodes to the right of a node are greater than it. Okay, and you can flip those around if you want. Just be consistent. Yeah, don't randomize whether it's the less than or equal to thing or whatever. So you choose how your trees are going to be built. There is probably a formal definition. I think this is it. I think it's less than or equal to the left and greater than to the right. The other way? Well, the book's probably wrong.
It could be.
Yeah, I mean, and it's entirely possible if the book does have it the other way, that's not the official way. That's just the way they wrote it as well. So somewhere, I think in the original, documentation for whoever came up with it first, they probably have the original standard. And it doesn't matter as long as you always do it the same way. Okay? It will matter if you don't always do it the same way. So kind of pick a favorite and go with it. All right. Now, let's draw a picture of a tree because I want us to recognize a few things about a tree here. And a word I'm going to use here, a phrase I'm going to use here that's going to kind of come back up maybe to haunt us soon, is this idea of, and this is really more of a Lippmann phrase, is pseudo-recursion. Okay, well, remind me, what is recursion?
Use a method inside the method.
Okay, so when a method is defined in terms of itself, or when a method calls itself from within itself. We've seen it with like merge sorts, and that usually gets initially introduced with like factorial, that kind of stuff, right? So it's when a method is introduced in terms of itself. What do you think I might mean? And we won't go too deep into this till we have an exact example, but just as an initial, thought-provoking question, what might I mean when I say pseudo-recursion?
Pieces of it.
So we're going to be doing something that's kind of like recursion. In fact, at a glance, it's going to look like recursion, but it's not exactly recursion. We are calling the same method, but it's actually a method owned by a different instance. That's kind of what I mean by pseudo-recursion. Because what we have here, and let me draw this picture first, and then I think it'll make some decent sense. And mostly because I like drawing. Oh, you should have seen the turtle I made in at the Grace meeting last night in VR. That was pretty legit, wasn't it? Who saw me make that? That was a good turtle, wasn't it? I had Donatello, and he had like sparkles coming off his bow stat. Oh, it's pretty good. Yeah, I'm just saying. All right, that's a tree. All right, so this guy might look, that's actually not bad. That's a pretty decent tree. Okay, so this is a tree. This is our root node, and we're going to go ahead and make this as a binary. So I'll do a 5. So this guy will be a 4. This guy will be a 6. Since we said less than or equal to, this guy could also be a 4. This guy would be a 3. Actually, oh, we're going to have trouble. Okay. So there's an example of a binary tree. So notice we have a 5 here, but it's in 2 different places, right? So we dropped that first 5 in when we already had the 6 there, and 5 is less than or equal to 6, so we placed it here. Now the last 5 was probably the last thing we entered. We dropped a 5 here. So Plinko, is this open? No. Is 5 less than or equal to 6? Yes, so we put it here. Is this open? No. Is 5 less than or equal to 5? Yes, we went to the left. Is this open? No. Is 5 less than or equal to 4? No. It's greater than, so we went to the right. Was this open? Yes, so we put the 5. That make sense? All right, so now an interesting truth about trees that is sometimes hard to grasp initially is this statement. A tree is a collection of trees. If I disconnected this piece right here, is that a tree? We pulled over to the side, we just looked at it just there, that's a tree. But when we were looking at inside of the entire collection, we wouldn't necessarily have called that a tree, correct? Even though it was. That guy was a tree. Is that a tree? Yep. Is that a tree? Yep. And we've called the whole thing a tree. So let's say, let's add we'll add another 5. That way we have to do the comparisons pretty often. So we're going Plinko mode. So I'm going to add a 5 to this tree. Can I add it there? Or is this spot already taken? Spot's already taken. So what do I do next? If you were to tell me in English what I now do with that 5, what would you say? Okay, that's the next thing. Yeah, so it is. It's less or equal to 6. So now that means I'm going to the left side, right? So now what exactly should I do? Would you say that the move I just made was I tried to add a 5 to this whole tree? The tree whose root node is 6, correct? Should I now try to add a 5 to the tree whose root node is 5? This guy's a tree, right? Aren't I making basically the same call I made to start adding this value to the tree? Again, but instead of doing it on the top level tree, I'm doing it on the left subtree. So I'm saying, okay, well, there isn't room to put this guy here, so I'm going to get this guy's left node, which is in and of itself a tree. We can call it a node if we want, but it's a tree. Okay? When we dealt with linked data structures, linear linked data structures rather, we had a bunch of nodes linked together, right? Well, now we have a tree of trees. This is a tree here at the top level. To his left is a tree. To his right is a tree. To this guy's left is a tree. To his right is nothing, is null. To this guy's left is a tree. To his right is a tree. So on and so forth. So I'll try to add 5 to this tree. If that doesn't work, which tree would he legally be added to? The tree to the left or the tree to the right? It'll be the tree to the left. So I'll grab the tree to the left. I'll say, I want to add this 5 to the tree to the left, which is a pseudo-recursive call, right? It's the same function I just called a second ago, which was add tree to tree or something like that. But instead of calling it on the tree with the pointer for 6, I'm adding it to the tree, which is the left tree of this guy. Can I put it there? Nope. Is it less than or equal to that or greater than that? It's less than or equal to it. So what am I going to do? I'm going to add it to the tree to the left. Can I put it there? Nope. Is it less than or equal to that or is it greater than that? It's greater than that. So what am I going to do? I'm going to add it to the tree to the right. Can I put it there? Nope. Is it less than or equal to that or is it greater than that? It's less than or equal to that. So what am I going to do? I'm going to add it to the tree to the left. But I can't just haphazardly say, this guy dot get left tree dot add tree with this, because this guy's left tree is null. So I have to ask the question, how do I find out if I'm allowed to add it there? Well, I say, do you have a left tree? If no, I found a home for the guy. I'll go ahead and set your left tree to this tree I'm trying to add. If no, I'll go ahead and tell your left tree, look, I need to find a home for this guy. Please add him. And now I've washed my hands of it. It's no longer my problem anymore. Even though it's the same lines of logic we're going through, it was owned by a different root node. Does that make sense? Okay. Good.
Would it be faster just to go compared to the 6? And then, is there anything that actually has to go, okay, it's going to go into the left side of this tree and then jump down to the last internal node, which would be the 4, compared to that instead of going through everything that's between the 6 and the 4?
Yeah, you probably could try. I mean, you'd have to keep track of additional pointers. You'd have to have pointers to the bottom of the tree. And then probably have to have your tree act like a doubly linked list. So you can crawl back up the tree, which is something we need to be able to do with, often need to do with self-balancing trees. So to your point, there may be some ways to optimize the adding, but it will make it significantly more difficult to rate add. Okay, so like right now, actually this is an interesting question. How many of you, if I were to ask you to write, create a binary tree and write the add function, feel that add would be pretty complex to write? Based on what we described. Not necessarily that you will find it easy, but the amount of code that you think it'll take to write. How many of you think it'll be complex? How many of you think it's going to actually be like pretty simple? There's not a lot to it. Okay, can I put it here? No. Do I have, where should it go? Left or right? It should go left. Do I have a left guy now? If no, put him there. If yes, tell him to add it. And it's calling the exact same logic again. So really, it's an if statement. I mean, it's really not a whole lot of work to add something to a tree. So what you're saying is, would it be faster? Potentially, but you probably add a lot of complexity to the implementation. So then it kind of comes back to this idea of, in your particular application, which is happening more often, are you more often adding stuff, or are you more often looking for stuff? And that might play into how much time you spend A, optimizing the tree, and B, optimizing adding to the tree. If you're usually adding stuff and on occasion retrieving stuff, but really the amount of time, you have 3 people using this and you're not really adding that much stuff, maybe 2 customers per day or something like that, just add it. Don't try to do any sort of weird fancy thing. Just add it. Move on with life. All right. So let's talk about the objects that we'll need for a tree. Okay, so a tree object. Okay, a tree object has a payload, so a value, right? Okay, so we'll call it payload so it kind of matches up to what we had before. That payload will be of the type we're storing in this tree. So maybe we start off with integers, so we're, because they're easier to do the less than or equal to stuff, right? So we'll have an int payload. And then we'll have what other attributes do we need to have for a tree object based on what we discussed the last few minutes? Okay, is it a node? What's a node? Tree. So we're going to have a tree, left tree, and a tree, right tree. Okay. What about functions? So that's going to be adding stuff there. Or that's going to be how a tree holds its structure together, right? Because you could call them nodes if you want, but since I've advertised it as effectively being a tree of trees, you could implement this as a tree data structure that holds a top node, which is kind of how we've treated linked lists, right? Linked lists is an object which holds a variable called head, which is a node that points to the beginning of the list. So you could certainly implement binary trees that way. Similarly, we can implement binary trees as a tree which holds other trees, where a tree is just a value, a payload. So the simplest tree is a payload that has nothing in it. Right, so we probably have 2 constructors for this guy. One that allows you to do an empty tree, and another one that allows you to start off a tree with the initial value, the initial payload. And then so now we're going to probably have add payload. And what will add payload do? This guy will try to add a payload here. Let's do that in caps. So that means set the payload for this guy to a value. If it can, we are done. Otherwise, decide which subtree it would need to be added to and try to add it there. Makes sense? Now, if we were building an Android interface for this, first of all, one thing we're not going to do is we're not going to try to actually draw the tree in Android. That becomes problematic. Not that it can't be done, but we'll end up spending a lot of extra time to get something to look like a tree when it really doesn't help that much. All right, but we'll still have a way of exploring our tree through our application. So how might you suggest us to have because I want to build a Android interface that's similar to what we did here, where we have an input box where we can have an add node, and we click add, and then we see it drop through our tree. How might we implement that? I mean, like, what do you imagine that app looking like so that we can kind of experience the tree? Because ultimately, you want to know where a node finally landed, right? So one thing we're going to say for a tree here is a tree is going to have a string called lexical address. Okay, and we all obviously know what that means. All right, so just like, if we look at our tree here, this guy, each one of these nodes, and we think about this like a block in your subdivision or something like that in real life. This house has an address, this house has an address, this house has an address, right? All right, so to give a lexical address for this, and there's kind of a formal way of doing a lexical address, but if you were coming up with a way of uniquely telling me where this particular node was in the tree, what might you say? How would you give me the address of that guy?
Give you the level it's in and then left or right, maybe.
Okay, so the level it's in. So this would be level 0, level 1, level 2, level 3. All right. Now you said left or right. Let me add something over here. All right, so let's say I'm looking for, actually, let's do it this way. So this 7 is a left child off this guy, right? All right. I want the lexical address of this guy, and I want the lexical address of this guy. So by your definition, they'd be the same address, correct? Both of this would be level 0, level 1, level 2. Both are left nodes. So this is 2-1, this is 2-1, correct? All right, so how do we differentiate those two based on address? Because if you're the mailman and I want you to deliver to this house, you need to be able to get to that house uniquely, right? Just put the letter in both or just pick one. Seems like our mail person does do that sometimes. They just randomly deliver mail, just expect us to hand it off. The other day we got a divider card, like a yellow piece of plastic that says "Do not deliver." It's like a divider for the different houses. And we got one of those. No, actually, I went to get the mail outside. That was all that was in the mailbox. So at first I thought, is that all they? That's a pretty bad mess up, right? If that's literally all they delivered was the one thing they're not supposed to deliver. But then I noticed the flag was up. My wife had put it back out there to take it back. But yeah. So how are we going to uniquely identify these two guys?
Left. So 2 levels of left and right, I guess, is one way you can do it.
Okay. So this guy, so we're going to say this is level 0, this is level 1, this is level 2. So that gives us a depth, right? But then we want to give it a position within there. At depth 0, we have no positions, right? So this is the top tree. That's kind of a special case, right? At depth 1, how many positions do we have? 2. At depth 2, how many total positions could we have? 4. At depth 3, how many total positions could we have? 8 and 16 and 32, right? That kind of thing. So when we're here and we go from 6, we go to add this 7. So let's try to get the address of the 7. It's not here. So we went from 0 to 1. But since we went to the right-hand side, okay, we know that the values we're dealing with are going to be the right half of the values, correct? Okay, so if we don't find them here, so we know our current place that we're looking at is level 1, position 1 or position 2, depending on how you want to look at it. So let's do everything 0 based. So this is level 0, this is level 1 right here, and this is position 1 in level 1. This is position 0 in level 1. Okay? So when I went to the right, I knew that I was dealing with position 1 at that level. All right. Is this the 7 we're looking for? No, it's this one. So now I'm going to go to the left of this guy, but I knew I went to the right initially. Okay, so when I go to the left of this one, I'm at level 2 now, and there are 4 possibilities for 2, for level 2. We have possibly 2 children on the left and possibly 2 children on the right. Since I'm already on the right-hand side, my left child is actually position 2. Does that make sense? So this guy would have a lexical address of level 012, position 2. This guy would have a lexical address of level 2, position 0. That make sense? So if we kind of put that next to it here, we would say that this guy is 2, 0. And we would say that this guy is 2, 2. Is that a reasonable way of doing it? All right. So for your homework for Thursday, implement a Android application that builds a binary tree data structure under the hood based on an edit text that allows you to keep adding numbers to it. You do not need to handle lexical address yet. So prove to yourself that the stuff was added in the right order somehow. Okay, so effectively what you're doing for Thursday is you're creating your tree object, doing an add payload, and you're calling add payload every single time somebody clicks a button and you're reading in the number from that edit text. That make sense? You do not need to deal with lexical address yet. We'll look at that in class on Thursday because it is a little cryptic. All right, I will see everybody on Thursday. I'll see some of you tonight. If you have not already signed up for the hackathon, the deadline technically was last Friday. Professor Josh Locklear said he will take a couple of latecomers, so if you will commit to it this Saturday from 8 a.m. to 8 p.m., get your name to him like within the next 30 minutes because we're going to be finalizing teams by this afternoon. And I'll be emailing all the teams out so they can start communicating with each other about their projects ahead of the hackathon. All right?